Good evening, student. Today we will discuss about concept discussed in week 6, and we will also discuss assignment of week 6 which given in last semester. So first of all, I will discuss about the week 6 assignment. It will also help you to solve the question of ongoing assignment, and I will also discuss about the important concepts and your doubts regarding the lectures of week 6. Okay, so let me know. Just a minute. Somebody invited. Okay, so first of all, we will discuss segment 6, which is covered in last semester. Okay, we should start now. So first question is, what is isobestic point and how does it look like? Okay, so in absorption spectroscopy, what is the isobactic point and how it will look like? Okay, so four options are given. I will read one by one, and we will conclude that which answer is correct. So first option is, at this point a specific wavelength, wave number or frequency at which the total absorbance of sample changes drastically during a chemical reaction or a physical change of sample. So it is clearly written here that it change drastically. Okay, so it is not right option. Okay, we will move on second option. So lambda 1 and lambda 2 according to this option, but this is not correct. Then I will read option B. At this point, a specific wavelength, wave number or frequency at which the total absorbance of sample does not change. Okay, this is the right answer because absorbance of sample does not change. Okay. During a chemical reaction or physical change. So whatever chemical reaction is occurring in your sample, the point where absorbance does not change, it is called as isobactic point. So at this point, specific wavelength, wave number or frequency at which the total absorbance of sample does not change. So this is the right answer. So B1 is right answer. Let me in. Somebody is getting me. Texting. Okay. Then these are the two. Okay, we already found the right option, which is B. Let me read another option. So option C is, at this point a specific wavelength or frequency at which the total absorbance of sample does not change during a chemical reaction or physical change of the sample, but wavelength change. Okay, so no, means absorbance not change means wavelength also not change, and total absorbance also will not change. Okay, so this C is also incorrect option. And finally D is, at this point a specific wavelength does not change during a chemical reaction or physical change of the sample, but wavelength or frequency at which the total absorbance of simple change. Okay, so total absorbance also will not change, so the point D is also incorrect. Okay, so for this question, what is the isobactic point and how does it look like? So B is right answer. At this point, a specific wavelength, wave number or frequency at which the total absorbance of sample does not change during a chemical reaction or a physical change of sample. Okay, I think it is clear. Any doubt you can ask. Okay, if you have any doubt, you can ask me. Okay, you can text me or you can raise hand, and we will discuss about your doubts also. Okay, so if you have doubt now, you can ask, or while my teaching also, if some doubts are created, then also you can ask. Okay, question number second is, what is the range of mild infrared region? Okay, mild infrared region where we run IR spectroscopy. Okay, so it is also discussed very well in class. Okay, so it is in between 1400 14,000 to 400. Sorry, it is not. Yeah, it is 14,000 to 400. Then B is 4,000 to 400. C is 400 to 10, and D is 1500 to 3000. Okay, so generally spectroscopy, IR spectroscopy run between 4000 to 400. Okay, so option B is correct answer. Okay, question number 3, which material can be used as an optical material in IR spectroscopy? Okay, so optical material means you are going to analyze your sample. Okay, so you are going to use some cuvette, or some, you can say simply a pot where you can put your sample. Okay, so this cuvette, okay, or test tube, or whatever you are using for analysis, this this thing should not absorb any IR radiation, otherwise it will interrupt your results. Okay, you will not identify due to disturbance of peaks created by material used in IR spectroscopy. Okay, so only analyte peaks should be there. Okay, so we will use material which will not absorb any radiation, or we can say this material should be transparent in this IR spectroscopy. Okay, so this material can be used for IR spectroscopy as a sample pot or cuvette. Okay, so many this type of materials are available which do not absorb IR radiation. Okay, and it will give a transparent meaning, like means what we can say, like glass. Okay, glass will glass will not restrict to pass light, na. Same thing, this material will do not restrict, okay, to IR ray. It will pass easily. Okay, so these are the material: lithium fluoride, cesium iodide, and KBr. So these all materials are being used in IR spectroscopy for optical materials. Okay, why these materials are only used? Okay, I have already explained, because this material will not absorb IR radiation. Okay, so that's why it is very useful for IR spectroscopy. Question number 3 is clear. Okay, then question number 4, in which titration method the indicator eriochrome black tea is used? Okay, eriochrome black tea means it is used, obviously it is used in complexometric titration. Okay, because in complex this will give a particular color which will useful to analyze the end point of your titration. Okay, question number 5, what criteria need to be fulfilled for the slope ratio method? Okay, slope ratio method. So it is forced to completion reaction. Yes. Okay. What in a slope ratio method, which is okay. Do you know what, if you if you went through the video, okay, where the slope ratio method is explained. Okay, so this method is used for measure the metal complex ratio. Okay, what is the metal complex ratio? So first of all, this reaction is means what is reaction? Complex reaction. Okay, complex formation reaction you can say. So complex and formation reaction is forced to complete. Okay, how it is forced to complete means either we can increase the concentration of either we can take excess in ligand or excess in metal. One reactant should be in excess. So, okay, so this reaction assume that this reaction is completed. Okay, so it is forced to completion reaction. So first option is correct. Then B's law is followed. Yes, B's law should be followed. Okay, then also always we can measure the end point of reaction. Then only the complex absorb at the wavelength chosen for the experiment. Okay, so wavelength, which wavelength we will use? So we will use only the wavelength which is absorbed by particular complex. Okay, so these all three options are correct. Okay, so we can say option D are correct. All of the above are correct. Okay, so D is the right answer of question number 5th. Okay. Then question number 6, which parameter changes observed during the end point detection of photometric titration? Okay, so in photometric titration only absorbance is changed. Means photometric means what we are using. You are using light. Photo means the photon. Okay, light. So only change in absorbance. Yeah. Okay. Change in wavelength, change in pH, and change in potential. So change in absorbance is right answer. Okay. So absorbance. So change in absorbance due to particular concentration of element in your sample. Okay, so it will give result according to element or molecule present in your sample. Question number 7, the luminescence process which is longer lasting than fluorescence is called. Okay, luminescence means something is illuminating, means it is giving light. Okay, in longer lasting than fluorescence. Okay, so longer lasting means it will give color after some time. Okay, means what we can say, if you see the some watches which provide color in dark also. Okay, so the phosphorescence is responsible for color in dark. Okay, because molecules are present there which absorb light okay, and they emit light after some time. So in dark also, in dark it will also emit radiation, and you will able to see watch accordingly. Just a minute, somebody will take the mic. Okay, so the phosphorescence is the right answer of this question. We will discuss the theory behind the phosphorescence also. Okay, but now we are only discussing about the question answer. Okay, then question number 8, which among the following reagent can be used as a reagent for simultaneous spectrometric determination of lead +2 and aurum +2, means lead and gold. Okay, so how we can use simultaneously, it is also discussed in lecture. Okay, so I think you know about the answer. Okay, so here methylmeprazine hydrochloride is right answer. Okay. Okay. Then question number 9, the order of carbonyl stretching frequency in IR spectra of ketone, amide and anhydride is. Okay, so stretching frequency means, just a minute, let me separate the table. Okay, so stretching frequency means okay. So stretching frequency is what? Stretching frequency means if two atoms, if two atoms are making bond, okay. So how strong is their bond? Okay, if bond is stronger, then you need more energy to vibrate. Okay, so similarly, there are different type of molecule, and you can compare them. Okay, okay, which molecule need more energy, and how you can compare according to their bond strength. Okay, so amine, so I think amine is highest, require highest energy to vibrate. Okay, then ketone and amide. Okay, so amine is, anhydride is not given, it is amide I think. Okay, amine, at the place of anhydride please mention amine. Okay, so amines have highest required highest energy to vibrate, then ketone, and then amide. Okay, so let me discuss about, okay, I will discuss this thing also. Okay, if you have any doubt in this question, okay, if you I will clear this doubt in upcoming slide. Okay, but for time being, if you know, it's okay, otherwise I will explain. Okay, then question number 10 is, what is the wavelength of emission maxima of reduced form of NADH? Okay, so NADH is the full form is written here, nicotinamide adenine dinucleotide. Okay, it is found in your metabolism. Okay, and okay, it is found in metabolism of living being, and it is absorbed at 465 millimeter. Okay, it is not any conceptual question. Okay, you need to only memorize, so I will not go further. Okay, then yes. Okay, so from here I will discuss some important concepts. Okay, which I think you should have doubt. Okay, because it is not very easy. Okay, okay, so in this week number 6, okay, many things are covered. Okay, regarding metal ligand complex, how to find out metal ligand complex, then FTIR. Okay, first of all IR, then FTIR. Okay, so we will discuss then last fluorescence and phosphorescence. Okay, so we will discuss one by one, step by step. Okay, so chelating reagent, what is the meaning of chelating reagent? Okay, any chelating means uh, you are making complex. Okay, like EDTA, when metal react with ligand like EDTA, it makes some complex. Okay, so this chelating reaction, why, then second question will be rise in your mind, that why we are making chelating reagent. Okay, so chelating reagent will give color. How it will give color? Because they have some chromophores. Okay, so due to presence of this chromophores, they will give color on, and the color will be responsible for analysis. Okay, so this is the main motive behind chelating of any complex. Okay, then sometime mixture of analyte you will find. Okay, so if mixture of analyte is there, then you it can be mixture of transition metals. Okay, some inorganic species and non-transition metals. So generally transition metals like D group element, they have DD transition. So according to DD transition, you will able to identify them according to color and their oxidation state and many more. But if they are found in mixer, then it will be very hard to analyze. Okay, so what is that? We discuss about isobacteric point now. So I am just taking this graph B. if you, I think you will able to see, just a minute, pointer, yes, but, okay. So if you able to see this graph, okay, so this is the isobactic point, okay, which will not change according to reaction proceeding, okay. So this is the isobactic point, and if okay, so suppose this is the, here you are getting some peak, okay, second peak, suppose you are getting here one more peak, okay. So how you will calculate, okay, means how you will calculate total absorption. Okay. So first of all, you can say, suppose this yellow one is A species, the green one is B species, and this blue line is C species. So three species are present in your sample, and you are going to calculate total absorbance, okay. So I need to mention, suppose something else, AT, okay. So it will be different from A, okay. AT means total absorbance. How you will calculate, okay. Suppose you are calculating at this point, X point, I can say this is the X point, okay. So here are, okay, total absorbance at the T point, okay. So you will first of you will need to find its molar absorbability, which is epsilon, suppose it is A1, okay. So we can say epsilon of A, okay, at the X point, okay. Then B, B is nothing but thickness of your cuvette which you are taking for a sample, okay. Then it is a CA, means concentration of A, at that, okay. Then it is for A, then epsilon B, okay, epsilon B, then again it is only B and Lambert law, okay, B and C, so it is a concentration of B, okay. So we can say epsilon, you can write X, okay, here also dx. Then finally one more term will be there, okay, it is for C species, so it will be epsilon C X, then B will be constant and the concentration of C, okay. So like that you can calculate total absorbance at X point, okay. So it will be only Lambert law term, okay, and these three terms are for three species. So according to that you can find out the total absorbance, okay. Similarly you can find here also suppose this is the Y point, okay. So you can also calculate total absorbance at Y point, okay. Okay, so this is the one thing. Then so now we will discuss about this graph, okay. We have already discussed it. Then what is happening, suppose you have one more concept I need to clear, okay. So you have already discussed about the isobactic point. Suppose this is the pH, change of pH, okay. Okay, how pH is changing, like you are, suppose you are adding base, okay, suppose initially. So this type of curve, suppose you are getting here is, it is HIN, okay, and here it is IN minus. Why it is so? Because you are increasing pH, so your weak acid is changed now in negative ion, okay. H is consumed due to rising pH. but this point will never change, so it is called as isobacteric point. Okay, and this IN is changing due to the absorbance is changing due to IN. Okay, at this pH it will give this absorbance. Okay, so it will be due to color change, and you can identify. Okay, so this will not change, isobacteric point will not change, and only the color will be changed due to pH. Okay, initially suppose here it is blue in color. Okay, so blue color will be disappear at this point, it will be disappear, then at second point, so this is the first point and this is second point, so second point you will able to see another color. Okay, due to this absorbance, and according to your absorbance you can measure that your end point has reached. Okay, so this is the okay, then absorbance, suppose this is the absorbance. Okay, and you are going to, you have one metal MX, and you are adding some ligand. Okay. So they will form MLS, means metal ligand. Okay, it is forming metal ligand. So if this metal ligand is responsible for absorbance, okay, how you will found endpoint. Okay, so like that. Suppose initially suppose metal and ligand are not responsible for any absorbance. Okay, so they will get straight line. Okay, because metal and ligand both are not responsible for any absorbance, only metal ligand which will be responsible for absorbance, so you will get it like that. Okay, because when metal ligand will form, it will give color. Okay, then if suppose if metal and ligand is also responsible for absorbance, then it will be like that, then metal ligand. Okay, so here this line is for metal and ligand separately, and finally this is for metal ligand. Okay, so here also you can find out how the reaction is going. Okay, then absorbance change sharply. Acid base do not absorb indicator. Okay, here we can discuss about one example where your analyte has two ions which are bismuth, which are Be+3 and Cu+2. Okay, if your analyte has these two ions, bismuth and Cu+2, okay, and if you are going to measure absorbance, okay, so initially what will happen, because the formation of Kf value, for bismuth. Okay, suppose you are going to add some ligand like EDTA. Okay, when EDTA means making complex with bismuth, the formation constant or Kf for bismuth is around 6.3 into 10 power 22. Okay, and it is for copper is Kf for copper complex, when copper make complex with EDTA, it is equal to 6.3 into 10 power 18. Yes. Okay. So by this formation constant, we can say that this formation constant is very large compared to this one. Means bismuth formation bismuth complex formation constant is very large compared to complex made by copper. Okay, so this reaction will occur first. Okay, when this reaction will be completed, then only this reaction will be started. Okay, so we can say that first of all what will happen, because EDTA will try to react with bismuth first because its formation constant is higher. Okay, so initially if you will see, okay, so suppose here to here, okay, here to here means here EDTA is making bond with bismuth. Okay, but the formation when when copper react with EDTA, when copper react with EDTA, it will give absorbance. Okay, so when from here to here, sorry, it is EDTA. Here I need to write EDTA. Okay, this is the concentration of EDTA. So as EDTA concentration is increasing, initially the absorption is not changing. Okay, why it is not changing? Because EDTA is reacting with bismuth. EDTA is reacting with bismuth from here to here. Okay, so here all bismuth is consumed. Now copper will react. Okay, then copper will make complex with EDTA. So copper EDTA complex will give absorbance, and your graph will increase like that. Okay, but after some time, all copper ion will also consume. Okay, so finally you will get step down. Okay, because EDTA is not responsible for color absorbance change. Okay, bismuth is not responsible for color change. Only copper is responsible for, copper complex is responsible for color change. Okay, so like you will get this type of curve. Okay, by this curve you can identify, this is the first end point where all bismuth is consumed. Okay, so this is the first end point. Okay, it is due to bismuth plus 3, and this is the second end point which is due to copper plus 2. Okay, so by this data of this curve you can identify both end point. Okay, and which will be useful for analysis of your angle. Okay, any doubt you can ask in chat box, or you can unmute yourself and ask. Okay, then to find out, okay, to find out metal and ligand ratio. Okay, X is to Y we can say. Okay, so to find out metal and ligand ratio, different type of methods are given. Okay, which is also explained in lectures. Okay, so we will discuss one by one. Okay, and we understand how it will be calculate. Okay, so first of all, here you can say, suppose this is pure metal and this is pure ligand. Okay, or ligand means it is EDTA solution. For more simplification we can say it is EDTA solution, and I can write E for EDTA, Okay, and this is a solution of pure metal, suppose copper. Okay, it is copper plus 2 solution. Okay, so now what we are doing, suppose from here to here when I am moving left to right, ligand concentration is increasing. Okay, so when we will add ligand concentration, so complex will be formed. Okay, but uh, at one point ligand will found in excess. Okay, so this will be means this point where all ligand is consumed by metal. Okay, will give you maximum absorbance like that. Okay, this way. So according to that you can find stoichiometric mixture. Okay, and by this way you can find out mole fraction. Here you are able to get mole fraction of ligand. Okay, which will be this point. Okay, so it will be more mole fraction of ligand. Okay, similarly you can find out the mole fraction of metal. Okay, because 1 minus suppose it is 0.7. Okay, if ligand is 0.7, then metal will be 0.3. Okay, because overall it should be 1. Okay, total mole fraction should be 1 na? So it is 0.7, so it will be 0.3. So according to that you can find out the ratio. Okay, what are the metal ligand ratio. Okay, so the illustration below show a condition various plot for metal ligand complex between Fe plus 2 and orthophenyl orthophenanthrolene. As shown here, the metal and ligand form the 1,3 complex. Okay, so it is forming 1,3 complex like that you can find. Okay. So this method is known as continuous variation method. Okay, and here we will calculate absorbance, which we plot absorbance with ligand mole fraction, or metal. We can also plot with metal mole fraction also. Excel can be changed by XM also. Okay, it will give same result. The plot will be inverse, but you will get same result. Okay, so this is about continuous variation method. Second method is mole ratio method. Okay, mole ratio method means here we are going to find out. Here we are going to find out NL upon NL. NL means ligand upon metal ratio. You can say mole of ligand divided by mole of metal. Okay, and it is plotted with absorbance. Okay, so here you can see. Just a minute. So in first plot, the mole ratio plot for formation of 1:1 complex, in which absorbance is monitored at the wavelength where only a complex absorbs. Okay, so from here, as you are adding ligand molecule, the complex will start form. Okay, so absorbance will be increased, and it will be increased according to concentration of complex. Okay, as complex will be complex concentration will be increased, the absorbance also will be increased. Okay, and at particular point, okay, means all metal ions are consumed by ligand. Okay, and it is now metal ion is not present in the solution, so no more complex will be formed. So now the absorbance will be constant. Okay, because you only your complex is responsible for absorbance. Okay, so at this point no more metal, so no more absorbance. Okay, that's why the first curve can be find out the metal ligand ratio for 1:1 complex. Just a minute, somebody let me check. Somebody is texted or what happened. Okay. Okay, so in second curve, the absorbance is plotted with similarly ligand upon metal ratio, but here what is changed is so what is changed here? Here metal, ligand and metal ligand complex all are responsible for color change. Okay, then what will happen? Initial absorbance of metal. Okay, suppose this is the some metal concentration is there, so it is not zero. Okay, it is has some value, so it is starting from here. Then due to metal ligand formation, the absorbance will be increased. Okay, as you will move up, absorbance will be increased, and here after this point the slope is decreased. Why this slope is decreased? Because here metal ligand complex is formed here. Now all metal is consumed, so this absorbance is due to ligand. Okay, that's why this slope is decreasing. Okay, so by this way you can also identify the end point of metal and ligand. Okay, so it is also written here, the mole ratio plot of 1:1 complex in which all three species, the metal, ligand and the complex absorbed selected wavelength. Okay, then last C point, here two type of metal ligand is forming. Okay, initially 1:1 metal ligand complex is forming. After that, when you are adding more ligand, then it is Ml2. Okay, initially the ratio was 1:1, but if further adding of ligand, the ratio of metal and ligand change by 1:2. Okay, so here also you can say as here to here, this absorbance is due to metal ligand Ml 1:1 ratio. Then the slope is changed. Okay, and here also it is constant, and this absorbance, this region absorbance is due to Ml2. Okay, and this is the saturation point here. Okay, after that the absorbance is constant because there is no more thing which is however you are increasing the concentration of ligand, but ligand is not responsible here for absorbance, so only maximum absorbance will be at Ml2 only. Okay, so these are the different method where you can calculate metal and ligand ratio. Okay. Okay, then what? One more method is remain. Okay, which is slope ratio method. Okay, so what is the meaning of this slope ratio method? Is here you are going to this first of all, this method is for weak complex. Okay, so this method is useful for weak complex and applicable only the system where single complex is formed. Okay, only single complex should be formed, not like similar to our previous case like Ml1, Ml2, this type of case not applicable here. Only single complex should be formed. The method assumes that the complex formation reaction can be forced to complete. Okay, forced to complete means you are going to force it to complete. How you can force to complete any reaction? By taking one reactant in excess. Okay, so large excess of either the reactant, either it will be metal ion or ligand. Okay, and it should be also it should also follow Beer law. Okay, Beer law means it should be the absorbance should be directly proportional to concentration. Okay, then you can use this slope ratio method. Okay, so we will understand how the slope ratio method work. Okay, so for the reaction, suppose this is the metal, M mole of metal and L mole of ligand. When they will react, they will forming this complex MM LN. Okay, so they are making this complex. But as we have already discussed, we are taking one reactant in excess. Okay, so first of all, suppose we are taking L is present in excess. Okay, suppose we are taking ligand in excess. So what will happen? The formation, what is the formation constant of this reaction if we are taking ligand in excess? So the concentration will not depend on ligand concentration because it is already excess. Okay, so the formation constant, okay, formation constant of this reaction will be concentration of product. So concentration of product will be we can say Ma. Okay, this is the MM. This is the concentration of your complex. Okay, concentration of your complex divided by concentration of metal. Because why I am taking only metal? Because ligand is already excess. Okay, so its value will be 1. We can take concentration as 1, so it will not affect. Okay, so this will be the formation constant. Okay, now if you cross multiply here to here and here to here, so you will get this equation. Okay, where mm ll will be equal to fm just a minute. Yes. Okay, because f into m formation constant will be equal to okay, and if Beer's law is obtained obeyed, then am should be equal to epsilon b and concentration of this ligand. Okay, or you can write in the place of ml1 you can write eb1 fm and m. Okay, similarly in a plot of am with similarly if we are taking m in excess, okay, so only the at the place of am l will become. Okay, and here also same thing will be there. Okay, if you will able to calculate this equation by Beer law, you will get this equation. Okay, so a plot of AI with respect of FL will be linear. Okay, because a plot of AL absorbance with FL. Okay, concentration of ligand, because metal you are already taking excess. Okay, so it will be in linear. Similarly, the slope of straight line AM upon FM or AL upon FL, and the ratio of the slope will combining ratio of ligand. Okay, so this will be a linear graph. Okay, like that, and the slope of this linear graph will give the ratio of metal and ligand. Okay. So this I just want to rewrite this equation just a minute. Okay, formation constant will be it means formation constant of metal. So it will be equal to inverse. I just wrote a wrong equation. It will be concentration of, it will be just opposite now. So reactant will convert in product. So it will be N concentration of metal, then concentration of complex. Okay, it will be inverse because we are taking formation constant of metal, not metal ligand. Okay, so now if you will solve, then it will be if you cross multiply, okay, so it will be metal, concentration of metal, suppose it will be mm. Okay. Okay, then finally this Fm will be come here, so it will be mm upon Fm. Okay, so you will get this equation. Okay. Okay, now we will discuss about the IR spectroscopy, infrared spectroscopy. It is due to, okay, so it is due to different type of vibration. Okay, you can say stretching. Okay, so molecule which have dipole moment like carbonyl group. Okay, okay, so this bond will be responsible for some type of stretching. Okay, and it will absorb uh, radiation at particular frequency. Okay, and you can measure this frequency and it is specific for particular group. Okay, so by this way we can find out that which functional group are present in our group, like OH. Okay, OH, COH. Okay, so there are different type of functional group. You can identify that which functional group is present in your sample. Okay, so it's follow Hooke's law, and due to vibrational level changing, it will give different type. It will absorb, a molecule will absorb radiation, and according to that you will get you will identify that which functional groups are present. Okay, then FTIR. So FTIR is Fourier transform, okay, of infrared spectroscopy. Okay, so it is it will give you interferometer. Okay, interferometer will be used for FTIR and it will give interferogram. Okay, so for infrared spectroscopy signal which will be decoded by Fourier transform. Okay, so initially, just a minute. Slide. Okay, initially what will happen? signal amplitude, signal yes amplitude, single amplitude will be plotted with time. Okay, single amplitude will be plotted with time, and it will give infragram. Okay. Okay, so this signal will be modulated by Fourier transform. Okay. And finally you will get okay, which will be transmittance with respect to wave number. Okay, transmittance with wave number. Okay, so it will be measured in centimeter minus. So here transmittance means 100% transmittance. Suppose it is 1.0 means 100% transmittance. Okay, and if any species present in your sample which will absorb like that. Okay. Then again 100%, then it will absorb. Okay, so this type of peaks you will find out in your infrared spectrometer. Okay, so this suppose you are getting this peak. Okay, so this peak you can find out particular wave number. Okay, particular wave number for this peak, and this wave number will be responsible for some functional group. Okay, so it will be responsible for some functional group, and you can identify that which functional group is present in your sample. Okay, so there are different type of peak, and by interfering this peak you can identify that how much functional group are present, how many type of stretching present in your sample. Okay, suppose you are taking simplest molecule, suppose CH. Okay, it is chloromethane. Okay, one chlorine molecule is there, and then this is a CH bond. Okay, so there are 3 CH bond which will give you CH stretching. Okay, similarly this is the Cl bond which will give you Cl stretching. Okay, so you will get 2 type of peaks. Okay, you will get 2 type of peaks. Okay, suppose you are getting CH stretching like that, and then you will get a Cl peak. Okay, so if you are getting this, suppose this peak is responsible for CCl stretching. Okay, or this peak is responsible for CH stretching, then you will get idea, okay, which molecule is there in your sample. Okay, so you can identify your sample by this way. Then this is all done. Okay, so here by seeing this slide we can find out many things. Okay, so suppose if aliphatic like CH stretching. Okay, so CH stretching methyl and methylene. Okay, methyl will give 2960 and methylene will give it 2930. So what is the methyl and methylene? Terminal CH group like CH3 is methyl group, and like, okay, so So this is like that. So here this is known as a methylene group, and this is the methyl group. Okay. So this group also will give different type of stretching. Okay, where methyl group is giving 2960 and methylene is giving 2930. Similarly, alkenes means carbon-carbon double bond. Okay, alkene means carbon-carbon double bond, and here you can see that if it is vinyl. Okay, so alkenes means this is the broad range. Okay, 3050 to 1640. Okay, this is the broad range. But according to like vinylidene, okay, so range will be different. Okay, vinyl give 910 to 16400, vinylidene give 980 to 460. Okay, cis give different, trans give different. Okay, so range will be changed, but you will the a broad idea you can find out by this C double bond C stretching. Okay, then C alkynes, which is C triple bond C. Okay, 3 bonds are there, 1 sigma and 2 pi bond. It will give absorbance in between 300 2000 to 2200. Okay, then we are going to discuss about the aromatic. Okay, so mono, ortho, meta, para. Okay, so means if it is mono means mono substituted aromatic, it will give 750 to 700. Okay, ortho means these are the two substitution is there. Okay, like you can say. Okay, mono means only X. Okay, but ortho means 2X, like that. But both are at adjacent position. Okay, like meta. Okay, so 1X will be here, then another will be here. Okay, and para. So para will be just opposite. Okay, so 1X is here, then another will be opposite side. I am not able to write here. Okay, so how you can draw para? Whatever, it is not very clear, but you can just opposite side. Okay, it is not clear structure. Okay, so this is the para portion. So this according to substitution also you will get some variation in your absorbance of wear number. Then if oxygen groups are present like CO and OH. Okay, so if CO is present, okay, in ether it will give around 1100, where in alcohol it will give in 1100 to 3350. Okay, so this is the range. In alcohol also you will get different type of structure. Then carbonyl group. Okay, so in carbonyl group C double bond O is present, but according to other atoms are attached to carbonyl, like this is the CO group. Okay, but it has carbon has 2 more sides which can be attached with different molecule. Okay, suppose if these both are attached with carbon only, then it will be known as ketone. Okay, so it will give peak around at 700. Okay, but if it is aldehyde, means 1 carbon is removed by hydrogen. Okay, like that. This is the aldehyde. Okay, so if it is aldehyde, then it will give 2700 to 730. Okay, in this range. CH stretching will be at 2700, because aldehyde has this also, na, this stretching, CH stretching. So this stretching will be at 2700, where C double bond O stretching will be at 700, means the CH stretching is decreasing here. Okay, it is decreasing by 30. Okay, so decreasing means what? What is the meaning of decreasing? Means here it requires more energy, 730, but now after replacing one carbon by hydrogen, it is only 700, means it requires less energy to vibrate. Okay, and it is also responsible for, you can say, some electronegativity. Okay, so here carbon is more electro negative compared to hydrogen, so electron will shift toward carbon, and this C double bond O bond will be relaxed. Okay, so this, because electron density will come toward carbon and this C double bond O will be relaxed, so it will be able to vibrate at lower frequency also. Okay, so that's why it is vibrating at 700. Similarly as ester. Okay, so what is the structure of ester? We will discuss about ester just now. Okay, so it will be one oxygen will be here, then it will CSA. Okay, okay, so what is happened now? Now oxygen is there. Okay, at the place of carbon now it is oxygen. So oxygen is more electronegative compared to carbon. So electron will be pulled toward oxygen. Okay, so this C double okay, so partially it will be positive. This carbon will be partially positive. Okay, so this bond will be more strong because this oxygen will be pulled toward carbon. So this carbon double bond oxygen bond will be more stronger. Okay, so it requires more energy. So here you can see it will be absorbed at 740. Okay, so energy increased. Okay, similarly in carboxylic acid also, okay, it is 740. So according to that you can find out different type of things. Okay, then a nitrogen group like NH. Okay, NH is absorbed at 3200. Then amine, it is amide for, and for amine it is around 33 double check. Okay, like nitride it will okay, so if you see structure the electronegativity, then you will able to find out that which molecule will absorb at which place. Okay, so I think it is clear. Just wait for 5 minutes. Okay, then we will start. Okay, so here we can discuss about how the overall functional group will be placed in your IR spectrometer. Okay, so y-axis will be transmittance. Okay, and this is the wave number in centimeter minus. So like OH NS stage here, you can say it is a single bond stage. Okay, but it will give peak around 305%, means very high energy. Okay, it is due to the electronegativity. Okay, then CH stage will give around less than 3000, and around it is you can say 2400, sorry 2700. Okay, so this region will be responsible for CH stretching. Then this region is triple bond. Okay, nitriles, carbines, which will fall in this region. Okay, so first single bond stays, then triple bond, then here it is double bond. Okay, so all double bond like C double bond O, C double bond C, C double bond N will fall in this region. Okay, this region, and finally this is for fingerprint. Okay, this is very complex region of your FTI IR spectroscopy, but it will give fingerprint, means it is give fingerprint of your molecule. Okay, which will very useful to identify that which molecule you have. Okay, so this is responsible, and it is fall between 1500 to 500. Okay, this region is called fingerprint, and it is very important for analysis of your molecule. Okay. Okay, so see, carbonyl bond, C double bond O. Okay, and means the frequency, the carbonyl group, the frequency of carbonyl in FTR is around 1700 centimeter. Okay, but it is changed according to group attached to the carbon. Okay, by remaining these two valency. Okay, so if it is N100, okay, if it is N100 band, then it will give 810 acid chloride. Okay, N100 band to ester. Okay, so means this peak position will be shifted. Okay, according to different type of group attached to them. Okay, we have already discussed that how carbon, oxygen, if attached with this carbon, then it will due to electronegativity of different type of element, the peak of IR will be changed. But here one more point we will discuss, which is conjugation. Okay, conjugation means if conjugation is there, like in this example you can see. Okay, so this double bond can be shifted here. Okay, so when this double bond will be shifted from here to here, this electron can be shifted to our oxygen, because oxygen is more negative compared to carbon. Okay, so overall this carbon C double bond O, now it is single bond only. Okay, so means this bond is relaxed. Okay, why it is relaxed? Because now oxygen can take its electron, means oxygen can take both electron. Okay, and only carbon is attached with oxygen by a single bond. Okay, so that's why now this bond require less energy. Okay, compared to double bond, single bond require less energy. Okay, so its stretching frequency will be decreased. Okay, so similar thing you can similar thing is written here. Lower force constant. Okay, due to single bond, lower force constant will be there, and it require lower frequency. Okay, it will require lower frequency. So similarly here in this example you can see, here also conjugation will be there. Okay, so the frequency is decreased 1715 to 1690. Similarly, 725 to 700 and 710 to 1680. Okay, so the why frequency is changing? Frequency is changed due to conjugation. Okay, so there are many type of example you can understand. Okay, so before moving further, we will discuss some more concept. Okay, in IR, FTIR, in FTR instrument there are different type of parts. Okay, like source. Okay, then transducer. Okay, so we have already discussed that which type of wires we should use. Okay, which should be made of material which should not responsible for IR range, absorbance. Okay, it's this material should not use IR range. Okay, otherwise it will give it will make it will create difficulty to analyze your sample. Okay, here also transducer, it can be pyroelectric or photoconductive. Pyroelectric means it will create electricity due to temperature. Okay, and the example for this type of transducer are triglycerin sulfate, and photoconductor are photoconductor, and the second type of transducer is photoconducting, so which will convert light into conductivity. Okay, so this is the example of this type of transducer is mercury cadmium telluride. Okay, then fast Fourier transfer, where amplitude signal is converted in power, and finally power is converted in frequency. Okay, then now we will discuss about the fluorescence and photoluminescence. Okay, so it can be on atomic level or molecule level. Okay, so how it will be happen, I will discuss step by step. So here suppose you are providing, so these are the energy state. Okay, S0 and S1, these are the electronic energy state. But here you will also able to find out some vibrational energy state. Okay, suppose this is the V0. Okay, then V1. Okay, then V2, it is V3. Okay, like that. So some transition is also possible. Okay, what will happen, we will discuss step by step. Suppose some light is provided. Okay, an electron is excited from ground state to this state. Okay, in S0 to S1, but it is not just threshold of S1. Okay, it is it has more, it absorb more energy. Okay, compared to S0 to S1, because how much energy it required, only this energy it required. Okay, but if you see, it is absorbed little more energy. Okay, so now this energy will be emitted. Okay, like that, and finally it will come on H0, H0 and V0. Okay, so this here also it will emit energy, but this energy is not radiation energy. Okay, this energy is loses by phenomena like collision. Okay, finally it will come here, and then it will jump to the lower state, ground state again. Okay, so if molecule relax molecule first relaxed due to vibrational relaxation, okay, and finally it will come from excited state to ground state, then it will absorb, then it will emit energy in fluorescence, because this is the instant process, okay, because this vibration relaxation is very fast due to collision, and after that this electron will jump again from higher excited state to ground state, and it will emit energy, okay, it will emit energy H. Okay, so this is the first case, which is known as fluorescence. Then how phosphorescence is different from the fluorescence. Okay, so fluorescence we have already discussed. Now we will discuss about the phosphorescence. Okay, so in phosphorescence, what will happen? The electron change in ISE means hello, sorry, it was okay. So what we are discussing, that in phosphorescence, what will happen? Electron is changing its state, okay, singlet to triplet state. So what is called intersystem crossing, okay. Intersystem crossing means electron is changing from singlet to triplet state, okay. So in triplet state, so here in singlet state, what is different between singlet and triplet state? In singlet state, both electrons spins are in opposite side, but in triplet state both spins are in same side, okay. So it is changed in triplet state. So now again from triplet state to okay, so now electron in triplet state, so when it will change in ground state, it need to change its state also, so it will take some little more time, okay. So that's why the lifetime of phosphorescence is higher compared to fluorescence, okay, because it is converted in triplet state, okay, due to intersystem crossing, and finally it will convert in triplet state, and finally again from triplet state it will convert in ground state, which is singlet state, okay. So it will take more time, and it has more lifetime, so it will give different color. But one you can say limitation of this thing is only few materials are phosphorescence active, okay. So this is one limitation. We cannot enumerate all the samples or all enumerate by this process, otherwise it is very useful, very sensitive, okay, and it can be higher sensitive, and it will also give linear range with concentration, but the limitation is only it will only some molecules are phospholuminescence active, okay. Okay, so this is all about second week, sorry, sixth week. Okay, and I have already discussed about this assignment questions and all the concepts which are typically new for this week. Okay, so any doubt regarding this thing you can ask. Okay, student, we will discuss little bit about assignment. Okay, I will not provide an answer, but we will only read this question and go through it. Which complexometric indicator is used to determine of metal ion bounded by EDTN solution? Okay, so it is already discussed many times. Okay, very simple question. Then fill in the blank with the suitable option given below. In AI spectroscopy, KBR is used. Okay, it is also discussed in my this class only. Okay, and this question is similar to previous semester question. Okay, so you can correlate this. Why KBR is used. Okay. Then question number 3, which criteria are needed to fulfill the slope ratio method? Okay, slope ratio method, this is also discussed. Then what is the range of fingerprint region is infrared spectroscopy? So whole range of infrared spectroscopy is discussed in this class only, and from there you can correlate this answer. Okay, what is the wavelength emission maximum produced from of NADH? Okay, it is also discussed. Then question number 6, which luminescence process is longer lasting than fluorescence? Okay, so you can correlate like that. Okay, which process need more time? Okay, which process need more relaxation time, lifetime is higher, then you can correlate that this process is known as what, and according to that you can answer. Question number 7 is, which one is the correct statement from the slope ratio method? BS law is not followed, which is correct. Okay, only it is not applicable when single complex form. It is applicable for weak complex reaction. This method is useful for complex, strong complex. So all the requirement for the slope ratio method is already discussed. Okay, and according to that you can answer this question. This is very simple. If you go through this class, then I think it is very simple. You can answer it very nicely. Then what are the two X's in the IR spectrum? Okay, so IR spectrum I have already explained. From there you can find out that which are the two X's in IR spectrum. Okay, but don't confuse with interferogram. Okay, which is finally decoded by Fourier transform. Okay, so X's are different for these two cases. Okay, but you can find out the answer very accurately for this question. Then question number 9, which instrument is used for the IR spectrometry? Okay, so different type of instrument are there. Okay, which is already discussed in class. Okay, some of them are used for qualitative purpose and remaining of them are used for quantitative purpose also. Okay, so this also you can answer. Then question number 10 is, which one of given below is used for IR source? Okay, so different type of IR source are there: nuts, blower, glober, nichrome, coils. Okay, so according to that you can answer. So the questions are very simple, and we expect that you will submit this and score very nice, because all question answers are discussed. Okay, in this class only these answers are discussed, so you can go through it. Okay, so symmetric stretching, asymmetric stretching we also discussed. Different type of instruments which are used for qualitative as well as quantitative purpose. Okay, so for this instrument, okay, for UV and visible, okay, UV and visible spectroscopy, we discussed that. First, a monochromator is there. No, we can get first source, okay, source of light. Then it will pass from monochromator. Then it will pass from sample. Okay. Then you will able to detect it in detector. Okay. So this is the overall structure of spectrometer of UV visible. But in IR, it is little changed. Okay. So first source light will pass from sample. Okay, then it will pass from monochromator. Okay, so all the scattered and emitted light will be not passed from monochromator, and it will finally go for detection. Okay, so window lenses and mirrors, okay, which are used here, it should be transparent. Okay, from 200 nanometer to 30,000 nanometer, like that. Okay, so there should be enough for that. Okay, different type of sources are also used for IR spectroscopy. Okay, first of all, it is nuts glare. Okay, it will give radiation from 400 to 2000 nanometer. Okay, and it is made for zirconium and yttrium oxide. Second is nichrochrome wire, which will give 750 nanometer to 2000 nanometer. Okay, it is made nichrome wire means it is made from nickel and chromium, nichrome wire. Okay, so then third is global source, which will give 1200 to 40,000 nanometer range, and it is made of silicon carbide rod. Okay, how it will work? When it will heated till 1500 degree centigrade, it will be glow. Okay, and it will also give radiation of this range, which can be used for IR detection. Okay, so FTIR spectrometer, all wavelength together, if we are reading all wavelength together, it will form a interferogram. Okay, and by a Fourier transform, it can be plotted with time domain spectra or frequency domain spectra. It is depend on our requirement. Okay, and by Fourier transform, by FTIR means Fourier transform infrared spectroscopy, you can find it out different type of functional group. Okay, and okay, first of all, you will able to find a functional group. Okay, then another is fingerprint region, FP we can say. Okay, fingerprint area, from where you can find out that which molecule is there. It is identical for particular molecule. Okay, so there are two things. First is finger functional group, where you can identify different type of functional group which are present in your molecule, and by fingerprint region you can find out that which particular molecule is present in your. Okay, so finally you will be able to identify this. Okay, so I think I have covered all this point of this class. These 2 points are remain left, so I covered now. Okay. Okay, student. Uh, I think you do not have any doubt. So we should stop here, and we will meet next week. Till then, bye. Thank you.
विद्या मार्कर